Hello and welcome to the Unit 10 podcast on section 16.5. Today we're going to be talking about spontaneity of reactions. I'm Mr. Sakaguchi,
And I am Mr. Lin.
and let's get started. So spontaneous, this is something whether that occurs on its own without any outside intervention. Energy normally is necessary to get the process started, but not to continue it.
So, enthalpy that we went over previously is one factor that influences spontaneity, but there are other ways for a spontaneous reaction to occur, and it's not always that exothermic processes, such as ice melting, is necessarily spontaneous. There are other ways for it to be spontaneous.
Right, so ice melting is endothermic with respect to the ice, so that's how we know that it's not always going to be just delta H that determines spontaneity. So the other factor that we're going to consider is something known as entropy. Entropy, which is symbolized as S, is basically the measure of disorder or randomness within a system.
Chaos.
Entropy can be predicted by changes of state. So the idea here is based upon the law of disorder. Spontaneous processes always will proceed with an increase in entropy.
So, in other words, it's natural for things to get messier and messier. This is known as the law of disorder or the second law of thermodynamics. And you know this simply by, I don't know, looking at your bedroom. Unless you work to keep it clean, it will slowly and progressively become more and more messy.
How do we predict changes in entropy? Well, we can look at changes of state. Go ahead.
So, for instance, you can go from a solid to a liquid. You have something that just sits there to something that can move around, and that's definitely more chaotic. So that's definitely an increase in entropy.
For instance, if we dissolve a gas in a solvent, this is a decrease in entropy.
Right, because the gas particles are slowing down. So, assuming that there's no change in the physical state, the entropy of a system can also change when you look at the number of particles, in this case, in the number of particles of gas. If it's a greater number of gaseous particles in the product side than the reactant side, then there is going to be an increase in entropy.
And when we're dealing with solutions, we can look at the solid or liquid solute, and we can determine whether or not the entropy increases for that as well.
Generally, if something is getting dissolved, if a solid or liquid is being dissolved, then it will increase in entropy. And then, like we stated earlier, gas would be the exact opposite.
Temperature increases will always result in increases of entropy.
Right, because there's more particles moving about.
So we can actually quantify entropy as opposed to just talking about it qualitatively. We know that the change in entropy of the universe will always be greater than zero, and this will be equal to the change in entropy of the system plus the change in entropy of the surroundings.
So the entropy of the universe is going to be positive for one of two reasons. First one being that if a reaction or process is exothermic, then you can be fairly certain that the delta S of the surroundings or the entropy of the surroundings is going to be positive because the surroundings are gaining energy.
And also it'll be positive when the entropy of the system increases, so the system is positive.
Right, so that happens usually accompanied with an exothermic reaction, and this is going to increase the entropy of the universe.
And these tend to be spontaneous.
Yeah.
So Gibbs free energy is a way to actually look at a numerical value, taking into account all the major factors that contribute to spontaneity, and this is known as the Gibbs free energy value.
So what you wind up doing is, with the equation below, you take a look at your enthalpy of your system, and then you subtract that from the temperature change, and you subtract that from the temperature in kelvins and the change in entropy of the system. And if you get a value that is negative, then the reaction is going to be spontaneous.
So we can look at different kinds of conditions for delta H, delta S, and for T delta S, and determine whether or not something is going to be spontaneous or not spontaneous. What we find is that if we have a negative delta H, a positive delta S, what's always going to happen is delta G is going to always be negative. So under these circumstances, it's always going to be a positive. It'll always be spontaneous.
Right.
If you have a positive delta H and a negative delta S, your delta G is always going to be positive, so that will result in non-spontaneous reactions no matter what the temperature change is. Now, go ahead. You can do the last.
After this, it's a little bit more dependent upon the temperature. So if you have a low delta H and a negative delta H and a negative delta S, if the temperatures are low, then it's going to be spontaneous, and if the temperatures are high, then it's going to be non-spontaneous. And then again, if the delta H's and the delta S's are both positive, it's going to be dependent upon the temperature again. So if the temperatures are high, it's going to be spontaneous, and then if it's not, if the temperatures are low, then it will be non-spontaneous.
That's right. So how do we calculate these changes? Let's say I gave you some numbers, and we have to determine whether something's spontaneous or non-spontaneous. So let's say the system is negative 75.9 kilojoules. The temperature is in kelvins, 273, and the entropy of our system is 138 joules per Kelvin. And so to make everything equal to kilojoules, we divide it by 1,000. So that's why we change it. Right. Then we can go ahead and use our free energy equation, and we find that when we plug in these numbers, we get a negative value for delta G. So we know that the process is spontaneous.
Right.
And this tells us exactly how much energy is liberated to either heat something or to do work on something else.
So in nature, what happens a lot are something called coupled reactions. And what this means is you'll have a non-spontaneous reaction being driven or pushed by a spontaneous reaction. So what happens is during the spontaneous reaction, it has excess energy and it bleeds off this extra energy, and the non-spontaneous reaction picks it up and uses it to do its own reaction. You find this in things like the electron transport chain, as well as things like photosynthesis in biology. An example below, the formation of creatine. The formation of phosphocreatine is drives the formation of ATP.
That's right. That's it.